All right, week 102 of building my own operating system. What's up, everyone? Welcome back. And let me just get set up. Got the ping in the Discord. And okay, today we'll keep it going with virtual memory. We had kind of a nice point of progress last time. So last time we were able to get the kernel running on its own page tables. And that was kind of a nice accomplishment. The goal for a while was to start migrating off of the bootloader's page tables. And also, let's get the music going. Yeah, and I'm actually sort of reconsidering that now, but in general, towards that goal, I was building out some virtual memory management infrastructure. And we sort of used that a little bit for the first time in the kernel to kind of get that working. So I would consider that a bit of progress. All right, and then question is, where do we go from there? So yeah, like I said, I'm actually sort of reconsidering the approach a little bit. The approach, right, and just to recap that, the idea was to move off of the bootloader's page tables and kind of migrate away from the bootloader, which would technically allow us to reclaim the bootloader reclaimable regions of memory, which is where things like the initial page tables, the various limine requests, these pieces of data that are passed from the bootloader, the kernel command line arguments, the initial boot stack, all these things live in the bootloader reclaimable region. And in a really production and professional kernel, you would migrate away from these and then reclaim these regions, because it's just data that can then be allocated from like normal from these usable regions. But the thing is, I'm sort of considering that a bit of an optimization, and it's not really the most important thing to do towards what I'm kind of trying to do. If my goal is to just get a basic kernel running with some basic scheduling of kernel tasks, for example, migrating away from the bootloader is not strictly a requirement to do that. And as far as I can see, there's nothing really that wrong with just leaving and just running out of the bootloader reclaimable regions. And in a certain way, they just sort of become other parts of memory that's just simply in use by the kernel. I mean, maybe there's some things I'm not seeing there, but the worst that I'm seeing that can happen right now is that I just waste some memory. So that's sort of a bit of a change in direction. I'm going to recap that. So changes in direction, no longer unit test heavy approach, more prototyping, and prioritizing making progress and not currently, not migrating away from the bootloader memory for now. So those are just a couple of decisions I've been kind of making. Yes. Let me just clean up a couple of my open windows. But yeah, and that sort of leaves me with a bit of an open slate as far as how to continue. What's up, Dogginuwu? Nice to see you. Thanks for joining the stream. Okay. Right. So concretely, what are we going to do? I think concretely, we can still move forward with thinking about the kernel's virtual address layout, virtual address space. We currently just have the very minimal one that Limini set up for us. But we can think about how we want to design this further and what else we want to add to it. I'm just going to quickly review this. So this is just sort of debugging some notes about our progress towards trying to run on our own page tables, which I just said we're not really going to prioritize right now. What else did the roadmap look like? So this is sort of the virtual memory stuff. Unmap. The thing is, we technically don't even need unmap right now. That's really not the focus. And that can happen later. It's not the worst thing in the world just to have a virtual memory implementation that can only map, because the kernel is in such a kind of just infant state right now. Yo, what's up, Ismail? Good to see you, my friend. I hope you're having a nice Sunday. I'm having a pretty good one. Yeah, got a bit of a sleep in earlier today, did a bit of cleaning around the house, and now we're back at it here. All right, let's check the roadmap also. Well, what was I kind of thinking? Paging, virtual memory, migrating away, blah, 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 blah. I just was sort of saying, I think I'm not going to focus on this stuff. Just kind of proceed. It's all just kind of random stuff. Made some tea. I'm chilling. That sounds nice. Sounds like a nice way to spend a Sunday. All right. So yeah, that's where we left off last week. Kernel got running on its own page tables, and like I was just saying, it's cool, but actually it's not the biggest problem in the world to be running on the bootloader stuff. So what I want to do is I want to keep running on the bootloader's page tables, actually, just for now, since it's just kind of set up. And I think I just want to think about I just need to think about what happens next, actually, because it's sort of an open field. And I think actually referencing JOS is sort of what I want to do. Let's just take a look at the JOS init code and see what it does. Okay, so basically, blah, 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 blah. It's sort of here, memory. Yeah, so the first thing it does is set up memory. And the first thing that does, required for that, is setting up. So this is where it starts setting up its page tables. It sets up this recursive mapping. It allocates its physical memory kind of frame data structures for kind of tracking those. It allocates the storage for all the kind of tasks / environments / processes. So that is bootloader is just using this. How do I find that again? Bootloader is just using this kind of stupid bump allocator, if I recall correctly. None of this is really that important for us right now, but I'm trying to see. Okay, so now, now we get to page init. What this is doing is, it's just setting up the physical memory allocator, the page allocator. So that's also not really that interesting. And finally, here's where we start to get to more interesting stuff that JOS does. And so basically, we are somewhat already, in our version of the kernel, my version of the kernel, we are sort of like at this point. We have a frame allocator. We're not currently that interested in this kind of stuff. We have page tables that from Limony, but I'm going to keep using those. What's up, Awala? Give me some guilds. How to start OS building for sure. That's the best I can do for right now. But there's a bunch of resources there that you might find useful. Okay, boot map region, right? So then it starts layout.h. It sort of just starts making bringing this into existence, and just kind of creating these permanent mappings in the kernel's page tables. And so, but a lot of these things are very unique to JOS. Like mapping that environments thing into the address space. Okay, then the stack. Use the physical memory that boot stack refers to as the kernel stack. What's up, Yazalde? Nice to see you, man. Use the physical memory that boot stack refers to as the kernel stack. Right, so in JOS, the boot stack starts out as this thing that's embedded in the kernel itself. And then they sort of make an alias mapping. But the interesting thing, and then right. But I think the boot stack continues to be executed off of all the way through the boot process. And it's only, I think, on the first interrupt where we actually start running off of this thing. Let's grep for k stack top. And here's where that magic happens. So in the interrupt descriptor or something like that, that's where we start to specify yeah, on the interrupt, use that as the stack. So that could be an option for something to do. Set up the stack mapping. Okay. Ideas. Set up a stack mapping as opposed yeah. Set up a stack mapping that is not the limini boot stack in the physmap. What's next? Map all of physical memory. So this is the physmap, so we don't need to do that. Initialize the SMP parts of the memory map, which is per CPU stacks. That's a little bit more advanced, so we can skip that. Some check things. Switch to the full thing. And what's the purpose of this again? Also, what's up? Neo is studying. What are you going to name the OS? I don't know. Haven't really gotten that far yet. Yeah, I don't really want to name it too soon. I want to name it when I feel like it's ready to have a name. So it's just this OS, this anonymous OS. Okay, we switch into the page tables, but it's not really clear why, actually. I think it's just sort of like as a test to see if they were kind of set up correctly. And yeah, and then what does JOS do? It sets some more flags. I don't really know. I'm gonna jump to the AI. Summarize what these x8600 flags do. Yeah, that, I don't know. I kind of forget the purpose of these, and it's probably not that important. So basically, at a high level right now, I'm just trying to figure out what to do, actually, because we sort of reached a bit of a checkpoint last stream, and we can go a lot of different ways from that now. And so as a reference point, I'm seeing what JOS does. Okay, so interesting. Okay. So I feel like Limini probably sets up most of this for us. Write protect is kind of interesting. But also not critical right now. That's the one that triggers a page fault if the kernel writes to a read-only page. Yep. What's up, Kadar Codes? Nice to see you. I'm doing pretty well. How are you? Yeah, having a pretty restful weekend. Kind of nice start to the year. Okay, yeah, these are somewhat esoteric. Okay, I think my takeaway from that is that I don't need to think about that too much. Okay, so basically not the only really relevant thing for the moment here is mapping the stack. And that's actually somewhat actionable, and we could consider doing that. As a refresher, this is what our virtual address space looks like right now, as only 2 things in it. It has the kernel itself mapped like pretty high in the top, I think 2 gigabytes or so. And then we have this large region called the FizzMap, which just contains basically all of physical memory. And for example, and so with the stack, what we would do is we would add another one here. We would have like add another mapping here for the stack. Currently, we're running off of this sort of like boot stack, which I'll call it the mini boot stack, which Lemony sets up for us. But yeah, it'll be good to get away from that because it is kind of sketchy that it is in the FizzMap, because the FizzMap is just this basically massive read write blob that corresponds to over here, and all of the protections you get from virtual memory go out the window. Let's just double check. Does it not show you the permissions actually? I think it doesn't. This memory map does not. Oh wait, but that's not the point of the memory map. More, it's like this QEMU dump would show us that. And that's what we're looking at here. So here is the FizzMap, and you can see it's all read write. So it's this big blob of readable, writable memory, and it would be completely possible to just blow off the end of the stack if we allocate too many variables and do too many function calls and start corrupting other random stuff in physical memory. So it's a good starting point, but it is actually somewhat of a point to move away from that. Yo, what's up, Bizarre Zib? Nice to see you too. Thanks for joining the stream. Can you, in theory, damage your hardware if you touch bad things in the FizzMap? That's a great question. I would say the answer is yes. But, I mean, really all bets are off because, yeah, like the FizzMap, key thing to remember in the FizzMap, it's not just RAM. Like, it's not just RAM where you can, like, write data and, like, get it back. Hardware devices live in the FizzMap, because it's all of physical memory. And physical hardware devices live there. And so when you start doing things in certain places, you literally begin to interact with hardware. Now, whether you can actually damage your hardware, maybe that's a different question. I would say maybe in theory. I know that some people that do this, like reverse engineering stuff, like I know like these Asahi Linux people, they were doing a lot of reverse engineering of the Apple Silicon, like undocumented hardware. And I think like one way they did that is by literally just doing that is sort of like interact with these devices. I think it should be mostly safe, but you sort of never know. You never know how buggy the device is, and you also don't know if you're interacting with it in a weird way. So it's not something you want to be like randomly doing. Yeah, there was actually a great talk at CCC about this. They created a lot of really sophisticated reverse engineering tooling that would allow them to poke at like the hardware and, for example, reverse engineer how the serial console works and stuff like this. So yeah. Okay, so stack being round, that's sort of that's a possibility. And that's kind of interesting because then, I mean, yeah, like JOS doesn't do that much, and it just kind of gets going. And so we're already in a state where we can kind of just like do things. And then what does JOS do next? My code navigation is like so broken for some reason. Okay. Well, I haven't really been working with the JOS code base in a while. Okay, so now they get into env init, and that starts to get into kind of like this JOS specific thing, where they start they start creating and setting up their data structures for managing the tasks that run on the system. And actually, this function is super short. It just initializes this free list of these environment structures, and that's kind of it. And again, that's sort of a JOS opinionated way of doing it. And so we don't necessarily need to copy that, but as a general principle, set up virtual memory and kind of get things sort of set up there, and then kind of set up your task infrastructure or data structures, and then interrupts would be next. So yeah, let's just kind of get going with that first thing I was saying. Let's think about the stack. And again, what we're going to do is the kernel is just simply going to allocate a stack in the virtual address space. That stack does not get immediately used. Like the code that's doing this is running out of the boot stack still. We're going to set up the stack, and we're not going to use it until the first interrupt, as far as I understand. On the first interrupt, that's where RSP actually gets reset, and we start running out of here. And then we kind of never touch the boot stack again. And really, this should be pretty simple. I think the main decision is just like literally where should the stack be. Yeah. We just need to pick a number. So like we have, it's, I don't know, like terabytes of address space. We just need to pick a number somewhere. But back to my kernel. So yeah, and as a bit of a refresh, I've sort of abandoned my approach of trying to do this super like production, professional, clean or whatever, because I realized that is getting really in the way of the most important things of just making a lot of progress or making any progress. So I'm sort of changing a little bit of my approach to be a bit more scrappy, a bit more just trying to move a bit faster. And that is what brings us to here. This is the code we were running last time in an effort to migrate away from the mini page tables. Like I was saying, I'm kind of reverting this decision. Moving away from the bootloader data structures is an optimization to get back more memory, like kind of just like get memory available and free it up for use, which is not really the most important thing at all for me right now. And so what I'm going to do is I have this all kind of committed, and so we don't really need, this is just kind of an experiment. This is going to go away. And even this is going to go away. All is going to go. This was all the code, that experimental code that I wrote that was just trying to set up the kernel's own page tables. And so we're no longer doing this. What we are doing is we're still going to keep using this virtual address space VA. And one thing I actually think I did correctly, or at least kind of nicely for now, is I designed the virtual address space class such that you pass in a pointer to a PML4 table. An alternative design would be that the virtual address space allocates its own PML4 table. The nice thing about taking a PML4 table as an argument is that it lets the virtual address space class take ownership of existing page tables that already exist, such as the lemony page tables that we boot with. And so even though I didn't create the lemony page tables, I can still use the vAddress space to take ownership of them and continue to do mappings within them. And that's what I would like to do. So here's what we're going to do. We're going to allocate a kernel stack. And then just thinking about JOS, yeah, one more note on that. Yeah, sounds sensible. Yeah. Also, I was sort of inspired by the unique pointer in C++ with this design, where unique pointer takes a raw pointer, which it takes ownership of. Unique pointer doesn't force you to allocate on the construction of the unique pointer necessarily. If you want to do that, there's the make unique helper, but the basic unique pointer, it takes ownership of what you give it. And so I was sort of inspired by that. So I just loosely did it the same way. Okay. And I forgot what I was going to look at JOS for, but I think it's not important. What we need to do is we just need to choose a location for the stack. It truly does not particularly matter. What we can just kind of do is look at here. And we're looking at the page tables that I created, kind of that we're no longer using. I'm just going to recompile and rerun it. Okay, cool. So now we're back to looking at the lemony page tables, which we're just going to keep using. Oops. And straight up, my first just thought of where to put the stack is immediately below the kernel. We just have so, like, or I don't know, leave one page or something like that. Like, and one thing I'll also just kind of point out here is that from the kernel perspective, we can only use the top half of the address space. That's sort of how the classic way you do it on 64-bit x86 is. User space owns the bottom half, user space. Dude, I don't know, make it blue. User space owns the bottom half, the kernel owns the top half. The fizmap starts directly at the bottom of the kernel's portion of the address space and kind of occupies that chunk. The fizmap is there. The kernel itself is basically kind of towards the top. And then we just have the whole rest of the space to choose what to do. And I don't know, I could just randomly put it in the middle, but why would I do that? I don't know. I think I tend to put it kind of towards the top. So as a completely arbitrary decision, I'm just going to say, let's put it not immediately contiguous with the kernel, but let's put it like one page away. I don't know. That's it's sort of an arbitrary decision. One page just meaning like, okay, I don't know if in case there's some random bug where we're like, I don't know, like accessing parts of the kernel and we like overflow or underflow a bit below that. I don't want it to just like start going into the stack. We can add a guard page. And so as a completely, just kind of initial guess about how to do this, I'm just going to make that decision. And so, so what we're going to do is, and then I'm going to say, p stack top, and it's going to be the virtual base minus k page size, right? Virtual base points here. I'll just double check that. Virtual base is this f8 blah 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 thing, and that corresponds exactly to here. We're just going to take that, we're going to bump that down one page, and that's going to be the start of the stack. And so, and then I'm just going to map a range. And so, so now we're going to map one k page size, and we are going to, right, so this thing's going to be p stack top. And then the question is, where do we map it to, which is, which we haven't actually discussed yet. And the JOS technique of doing this, or I don't know, the JOS implementation was to map it at the same place in physical memory. Use the physical memory that the boot stack refers to as the kernel stack. And so we're just going to have this thing like, I don't know where in my diagram, the boot stack is like somewhere in memory, like the kernel is over here, the boot stack is over here, and all we're going to do is add one more aliasing mapping that sort of makes it also appear right here. And that's just the physical memory that we're going to use. Optionally, we could allocate another frame. Like, we totally have a physical memory allocator. Instead of just reusing that memory in the liminy area, we could allocate our own memory for it. But there really is no reason to do this. As far as our approach of just leaving the limiting memory where it is and never reclaiming it, it's a completely usable, reasonable page of memory for using for a stack. And so we can just continue to, because after our boot phase ends, we're never going to, we're just going, like, that's just kind of done. And then we move over here, but we can just continue to reuse that physical memory. No one else is like running in the boot stack at the same time. So let's just do that. And then then we just need to do a conversion, I suppose. And let me I'm always kind of curious to keep improving my AI skills. And so I'm just going to kind of try to make a prompt of it. So I'm just going to say, replace this with using the converter to convert wait a sec, let me think this through. So we want to obtain basically this thing, my arrow tool. This is the address we want to. Oh, and this is where we get into that And this is where, okay, wait. Yeah, so, yeah, last time we were trying to figure out how to remap the stack into our new address space, which required identifying the physical address of the stack. And we did it in this kind of hacky way, right? We did it by doing a register dump from the QEMU monitor to look at what RSP is, and then we copy and pasted that into the source code, and then did the conversion on that. Let's not do that. Let's do it the better way. And so we need to, so before I get here, we're trying to determine the physical address of the stack bottom, and I'll call it the limine stack bottom, and I'm not going to try to AI. I'm just going to see if I can do it myself. And so rather than copy and pasting, let's use inline assembly. And so we're always going to, what we need to do is we need to even just determine what is even the current virtual stack pointer. And once we have that, we can use the converter to convert it to the physical address. And so this is the 32-bit one. And so as usual, though, I don't know how to do this. So please generate a 64-bit version of this function. So we'll use inline assembly to read ESP. We'll align it down to the next lowest page size, and we'll run that through the converter. I'll get to the question. What's up, Reckless? I'll get to the question in a little bit. So, so now we have a read RSP. And so what we can do is, let's just try this out. So we're going to get, I'm just going to call it RSP, read RSP, same, I mean, I don't need to be so verbose about it really, but just for explanatory purposes, and I think, yeah, I've since added a round down function to the kernel. And so we're just going to round k page size. And so we're just going to round this RSP thing down to the nearest page size. And then, yeah, this is basically limine p, limine stack bottom. Right, and then use the converter to convert it. Is that enough? I'm wondering if we can do it. I just want to convert. I didn't want to type out this whole thing, but I think it kind of got the point. Yep. So yes. And what's the problem here? This thing takes. Okay, so this is a UN64T, and the problem is that this is also UN60. Okay, I don't even know. That's like long. We need to convert this to a void star. But is it not possible? Oh, I was getting tripped up in the types. Also, palm tree timer. I'm just gonna, we won't do it right now, but let's make sure to do that at some point. Okay, what's going on here? I cannot cast. Read RSP returns a UN64T, which is a reasonable type to return for this kind of thing. And then my round down function, okay, I'm just going to ask AI because I'm not really an expert on all this casting stuff. How'd you cast from UN64T to Voidstar? Reinterpret cast. That's always so disappointing when I need to go for the reinterpret cast. But I guess that is the case here. Okay. I'll get to the questions in one moment. And then we're basically kind of ready. And so now we go here and we're going to ph limine. As a reminder, the ph prefix I'm using stands for physical address. The p prefix stands for pointer. Yeah, it is finicky, and I mean, I've even been doing this for a while, and I don't know all the rules and subtleties around it. But also in my day-to-day work, I almost never use void stars. Void stars are much more like systems, like, I don't know, like working with raw memory systems kind of thing. But I think this is pretty much it. So map range, P, yeah, we're going to map P stack top. Except it's not, it's okay, P stack top, right? Then P stack bottom. The kind of tricky thing is, and also there's probably going to be a warning here when I try to do math on, oh, this is also, oh wait, this is also unsigned long, so it shouldn't have P necessarily. Okay. The tricky thing is when dealing with stacks is like the stack top versus the stack bottom. Our stack top is right here, but for the purposes of memory allocation, we always use the bottom of the page, and so we need to make that distinction. So stack top, stack bottom, and then now we've kind of figure out the physical address. So now we're going to say we're going to map a P stack bottom to point at the PH limine lemony stack bottom for K page size. And this should make a mapped the stack. And then we can just kind of inspect things here. So let's just kind of run that. Map the stack, then we got the info mem, and that did not, did not do anything, unless I need to re-engage, you know, and really these details are a little bit not so clear to me. Then I need to re-engage and reload CR3 now that I've made changes to the page tables, I believe. Let me just try running that. Okay, and we're boot looping. Dang, that's crazy. So that, something went wrong there. And let me get to these questions. Then we'll take a quick break. How can I quickly get to the same page as you? I don't know how to do it quickly, but what you can do is do this course, which is how I learned what I know, basically. Using C, I can make OS of mine. Byteword says. That's true. I would say that's a true statement. Yeah. Yeah. Okay. Let's just take a 20 seconds, and we're gonna get back to debugging this. Okay, What's up, the Roy? Okay, so things are obviously not working. I'm just kind of wondering, what if I don't have the map range call? I'm pretty surprised that was causing boot loops. So this should do, and this is still boot looping. And I don't even know how to get out of that now. Oh, that's why. Because, okay, wait, this is the totally wrong thing. This is the one that I allocated for use. Right, so back when I was trying this whole approach of like trying to make my own page tables, blah, 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 that's the PML4 table that I allocated, and that's the totally wrong one to use. When we create the v-address space, we don't want to do that. We want to take ownership of the current ones from Limini, which requires reading CR3. Let's just do that. And do I have... I do. It's RCR364. So RCR364, right? And hello, okay. And what does this take? It takes it as a fizz adder, which domain CR3. Okay. So this thing returns a UN64T no, yes, which is convertible to a fizz adder. And so, okay, so now let's just try this again. Now that we have that now kind of taken care of. So we're no longer working with a new set of page tables. We're taking ownership over the existing Limini page tables. And let me just try that one more time. And so this should totally work, except now we're going to say Limini CR3. Here we're like not doing anything. We should not be mutating the page tables in any way anyway. All we're doing is instantiating this class which takes ownership over them, and then like we do a bunch of other stuff that shouldn't matter. And so this should absolutely not page fault or whatever. So that looks good. And then now we can bring back the map range. So now here's where we're starting to mutate the Limini page tables and kind of add our stack mapping. And I'm predicting that this is not going to boot loop. Even better, let's check out the memory. And here we can see it. That's exactly what we want to see. Here's our new mapping. We can see that it starts at 2 pages below the kernel and has a length of 1 page and ends at the FFFFF. So that is completely what we want to see. So that looks great. So that looks pretty good. I need to know how to, what's the keyboard shortcut for making an arrow? So, just want to kind of document things a little bit that way. Orange is a good color. Except I can't, okay, that's annoying, whatever. Okay, but anyway, this is what we want. This is our new, this is our stack. What's up, NSG? Yeah. So actually, so I sort of changed my mind. Rather than trying to migrate away from the Limini page tables, I actually just decided I'm just going to keep using them, because to me, reclaiming all the bootloader memory is really not a priority. It's not really that important. And they just sort of work. And so, yeah, that was just sort of my idea there. And so now what I'm just starting to do is fill out a bit more of the address space, starting with a stack, which we will use for interrupts. So that's sort of the idea so far. And I chose to place the stack at a little bit below the kernel, but with a guard page in between. So yes, so that's kind of cool. Yeah, this is all getting a bit messy, so I'm going to go ahead and delete some of this code. And we'll make a commit, kind of a whip commit. Okay, add read RSP. And then we're going over here. Whip map kernel stack. Okay, what's up hex AS1F? Nice to see you. Okay, so again, back to the venerable JOS. So now at this point, we basically completed mem-init, our version of mem-init. And then, like we were saying, env-init, I don't know, that, yeah. That's about how they manage their task/process data structures. And I don't know, we can do it differently or whatever. It's not really that important. And that sort of brings us to trap, actually, which is about setting up interrupts. And yeah, I mean, I kind of wasn't expecting to get to that quite so soon, but we can totally take a look at what that's going to involve. So yeah, this is like both one of the most interesting and most fun parts of OS Dev, and also sort of most sort of involves a lot of infrastructure. What's up, Stanisau? First time here working on the topic. Have you ever delved into the Plan 9 OS? No, I've never. Never. Would be interested to learn more about it, but I've never tried it myself. I know there's this one text editor from Plan 9 that people continue to use to this day, though. I think some people in certain circles. One guy that was that started streaming around the same time that I did. I think he doesn't do it anymore, but he was streaming himself writing video protocol, network protocols or something like this, using the Plan 9 text editor, which was, I think his name is Oliver or something like that. But honestly, no. Yeah, I think it was called Acme. I want to say that sounds about right. Okay, so let's talk interrupts. What do interrupts involve? And so interrupts involve a couple of things. So as we're seeing here, interrupts involve setting up all of these IDT entries. Yeah. Interrupts also involve setting up, where is, setting up kind of a bit of assembly actually. And so we've sort of avoided assembly so far for the most part, but yeah, it's kind of harder to do with interrupts. And so, but anyway, so all these descriptors and so on. Yeah. Plan 9 port. Plan 9 software libraries to Unix systems. Oh, that's cool. Did not know about that. So have you done a bit of development with that, or like kind of tried running Plan 9 or stuff like that? Honestly, I didn't even know you could do that. I thought it was, I know so little about Plan 9. I just know it was like one of these old operating systems. Like it's from the 80s or something, right? I don't even know. Or older? I don't know. Okay. And then here's the per CPU trap in it. And a lot of this is more complicated because JOS at this point in the history supports multi-core. But the really basic version of this, I remember it was not like so bad. It's about setting up the TSS, which is this whole like complicated structure, but really the whole purpose of it these days is just so you can set where the stack pointer should be on an interrupt. That was my takeaway from what I learned from this. And so all this is just about setting a couple entries in the TSS. Shit, I missed some Twitch messages. Off market. Will you use your OS as your daily driver? Probably not. I don't know if we'll get that far. Also, what's up, Dapster? Using x86 assembly for part of your kernel, right? Perhaps. Yeah, probably soon for this interrupt stuff. Yeah, so far we've kind of avoided it. Plan 9 was created after Unix in Bell Labs. Right, so that's like really early. That's like early history of operating systems, I would say, right? Okay, so we set up our TSS. We initialize the slot of the GDT. Which is unfortunately this like very esoteric kind of thing. Load the TSS selector. All right, yeah, this stuff it's been a moment since I've thought about this, so I'll need to remember how that whole thing works. But then you do a couple just like fairly esoteric steps to set up these data structures, and that's kind of it. Then you load the IDT. So, and yeah, we might go back and reference these old JOS labs where they kind of explain parts of it, I think. So yeah. Okay, where do we begin? I think we begin with just, now it developed in the late 80s, released in 92. Oh, interesting. Okay, obviously I don't know when Unix was developed then. I sort of thought that was the 70s or something, but yeah, you can tell my history knowledge of that time is not the best. Let's just go in, let's just take, for reference, let's just go in and pop into, I think it was like lab 3 or something like that. Yeah. And also, we're doing it on 64-bit, so it's possible that things are different. I know more about Unix history than programming itself. How are you compiling x86-64 code on an M-series chip? Are you using Rosetta or Docker? What's up, Lane? I'm using Clang from Homebrew, which includes a cross compiler and allows me to generate 64-bit x86 ELF binaries, and then I am running them in QEMU. And so the reason Rosetta is not involved directly is because I'm not generating like a Mac OS binary to run on the system. I'm not running natively on my operating system. I'm running within QEMU. And probably Rosetta is not involved at all because QEMU is probably also compiled as an ARM binary these days. I got it from Homebrew also, I'm pretty sure. So yeah. Clang, the Clang you can get from Homebrew, or Clang in general, is like includes a lot of architectures in it, all like in one. And so yeah, it's pretty easy to use as a cross compiler. Okay, so now here we have our trusty MIT course for telling us how to do operating systems, and yeah. All right, and we're talking exceptions, right? So let's refresh ourselves on how this works. Interrupt descriptor table. Task state segment. And that's pretty much it. Types of exceptions and interrupts. And then I think the way we did it when I was doing the JAWS stuff is, I mean, at that point we actually had sort of a bit of user space going, but user space would immediately crash when I tried to do a system call. And to kind of, as a first step, I think we were using these binaries that would generate some basic exceptions, like a divide by 0 exception. Because that's a pretty easy exception to trigger, and also sort of set up a handler for. Okay, so what's a baby step I can work on right now? I can just try to, that would be the goal. I want to set up a handler for like the divide by 0 exception or something. Like, I think, yeah, divide by 0 exception. And then I want to be able to just kind of trigger that. Like in my kernel code, I will then execute a divide by 0 and observe the handler getting called. nested exceptions. The overflow or overall flow depicted below. Okay, so all right, 20 seconds. Feel free to stand up and stretch with me. Okay. What's this flow that it's talking about? Oh wait, no, this is just explaining how the implementation works, where we have all these assembly stubs. And they kind of all call into the stub, and the stub does a very minimal set of things before calling into a common handler. Right, okay, so yeah. Let's look at this set gate thing. Or really, no, let's handle divide error, right? Where is that? Trap entry. Right. So here's where we would need to get into a little bit of this assembly stuff. And I'm kind of tempted. I mean, wait, I think I literally trap entry. No, I deleted that. Okay. I was gonna say I was just tempted to kind of copy a bit of this. Fine. Jump to all traps. I mean, we don't even need to do it in such a fancy way with the macros to start off. We can just kind of hard code it for the moment. And then add the more fancy macros later, maybe. At a ultra minimum, I think we need. So I just need to make an assembly file. This is going to be like one of the first assembly files in here, I think. Yeah, new file. File. Okay, duplicate file. Let's call this, I'll call it trap.s. I don't know. Yeah, the thing is, maybe I'll wait on the AI to help me a little bit with this. And so, no, so, I'm just thinking how I wanted to do it. I just want to have something that compiles in the kernel like at all. Type name. All these tabs everywhere. I'm just going to do an infinite loop. And I'm just going to say Okay. Please integrate trap.s into the kernel build. C kern.cmake lists.txt. I mean, it might just be as simple as adding the source file, but I don't know. Let's just see if that even compiles. I sort of don't know. Okay. Make forward target. What happens if I have a syntax error? Does it fail to compile? Yes. Okay, good. So that is compiling. I'm just thinking, like, what if I wanted to just like try calling it from the kernel? Just out of curiosity. Like I would add a call, and then I need to add some kind of void my func. Something like this. Extern C. Something like that. And then can I, so if I try to run the kernel right now, will it infinite loop? That's my question. We should not see the map to the stack thing. Okay, I think that's working. Yeah. So that was just a basic test that assembly is even compiling and like, you know, doing anything. So that's sort of there. Okay, so trap no error code. And so in the case of the no error code, situation, right. In order to give a kind of consistent layout, we're going to push 0. That's what the syntax means, I think. Then push the interrupt number, and then jump to this common kind of thing. So I'm going to mostly replicate this. And so rather than my func, I'm going to call this, I mean, it doesn't matter. Call it int an entry or something, like interrupt entry. Does it need the underscore? That's sort of what I don't know, why it has an underscore there. Okay, you know what? Let's give the AI a try here. What do I actually want to do? So I want to do a first. Let me get my transcription going. Okay. Step towards setting up interrupts in my OS. Trying this thing called hyper whisper. It's a little bit slower than whisper flow. So basically I want to have an entry point that we're going to use for, you know, I think I'm just going to copy a lot of this stuff actually. So we're going to take this thing, and we're just going to take this thing. Oops. Why did that not work? Okay. And we're going to all traps. And what's t divide? We're not gonna bother with like anything fancy. It's 0. So this is exception 0. I'm just curious if I can go back to where we were doing this. Can I find any good screenshots of here? This is what we want. Yeah. Here's at least some kind of description of the yeah. So we're going with 0. Does this compile? Right. Okay. Port this to 64-bit. Honestly, I don't really know what that. Push Q. Okay, keep. So. Oh, sorry if I missed your question. Off market. Will you use your OS as your main driver? Probably not. That's my current guess. I don't know if we'll really be getting that far with it. I'm sort of seeing it more as like a research OS. I don't even know if I want to make it GUI. Okay. You know, I think what's kind of yeah, there's like all sorts of things you need, right? So you have the assembly stubs, and then you have the trap.c, which has the actual trap handler function, right? And then that takes a struct trap frame, which is something you need to define. So there's like a bunch of stuff that you need here. But maybe just going again step by step. And so we generated our handle divided by 0 stub, which is going to call into this. And then now we need to right, we need to create the rest of the trap frame. So maybe another approach is to actually define this trap frame structure. That actually sounds like a decent thing to do. I'm gonna call it trap.hpp for the moment. I know it once. And we can use this as a reference, but it's 32 bits, so does that matter? I want to quickly look at the docs. You know, it's so tempting just to ask AI to generate, and maybe we'll do that in a moment, but I'm just wondering about what the 64-bit, what it looks like on 64-bit. Like if I was, so this is looking very 32-bit to me. And now this is getting into shadow stacks. Okay. Exception and interrupt handling in 64-bit mode. Okay. Let's just take a quick look through what this has to say. Okay. Handling exceptions is similar to what was all like described, except a bunch of things. So let's talk about that. All handlers pointed by the IDT are in 64-bit code. The size of interrupt stack pushes is fixed at 64 bits. The stack pointer is pushed unconditionally. I think that's this whole thing. Let me see. Like this thing or something, the ESP. I'm just going to go back and review my notes here quickly. So when the interrupt happens, the stack is optionally reset somewhere. And actually, in our case, this is kind of interesting. Because in my envisioned scenario, I'll be triggering an interrupt from the kernel context. And so actually, I don't necessarily know if I don't think it will actually switch to that new stack that we set up. I think it will keep using the same stack. Regardless, wherever the stack pointer is, it pushes a bunch of data automatically. And that's what is at the bottom of this upside down struct. And that is, I want to say that's like this stuff. Below here, only when crossing rings. Okay, interesting. And that's exactly what that comment was saying in the docs. In legacy modes, this push is conditional based off of the privilege level change. And so you may or may not have had like this stuff pushed, I believe. Only if you're crossing rings. Otherwise the processor dumps, or I mean, in any case, then it dumps a bunch of other stuff. The flags, the instruction pointer that was executing from. So it's really not that much. And then this error code thing, this optional error code. And then our assembly smooths that out with this 0. Yes. And then lastly, our OS code itself pushes a few more things on here, like the actual number of the trap and the ES and DS registers, and I'm failing to recall why. Okay, 20 seconds, be right back. Okay, and the reason I think is and we push these in order to save the state of those segment registers which were running before the interrupt so we can restore them later. And I think that happens in push trap frame or something like that. It's an env run, I remember that. There's this thing called env run and pop, yeah, it's pop trap frame. And in pop trap frame, it pops ES and DS to resume the state. So, okay, so at a high level, backing up a little bit, the point is just to preserve the registers, basically, preserve the execution state. There's different parts of that. These segment registers are part of that. Probably a bit of the less important part of that. Pushing the actual register state is the more important part. That's what we do right here. But this is just as all about saving the register state. And then we prepare to actually enter the kernel, which requires moving the kernel's selectors into ES and DS as opposed to the user space ones. And then we sort of jump into the kernel. Okay, cool. So with all of this in mind, as a bit of a refresher of how this all works, I want to go back to these docs now. And so it was saying things are very similar, except some exceptions. So you point to 64-bit pointers, that makes sense. Things are pushed at 64 bits, so that's a key difference. Stack pointer is always pushed. The new stack selector is set to null if there's a change in privilege level. The IREP behavior changes. There's a new interrupt stack switch mechanism and a new, okay, so that's sounds important. Okay, let's kind of go into this. So 64-bit mode IDT are 16 bytes in length to provide a 64-bit offset for the RIP. Okay, 64-bit RIP allows a routine to be located anywhere there. So this is relevant. We're going to need to, dang, zooming all over the place. Interrupt stack table. Right, there's this interrupt stack table, I think, and that is a difference perhaps from this TSS thing. because with 64-bit they had the opportunity to, I think, remove some of the legacy cruft, such as the TSS. Yeah, the IST is used by the stack switching mechanisms described, blah, 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 blah. Okay, so this is actually reasonably different from the 32-bit interrupt handling. In canonical form. Yeah, the RIP is like divided into 2 chunks. Okay, so the IDT is one thing. The RSP0 in TSS is the default kernel stack. ISTs can be defined for special interrupts. Oh, for example, IPS or fail. Oh, interesting. So you can still use the TSS. Good to know. What's up, Idahaka? Off topic, they're talking about your productive tips. I mean extension on browser apps. You mean like what tools I use, like what browser I use, or like developer tools or stuff like that? I have not made anything like that yet, but I could consider it. Okay, let's talk the stack frame. Yeah, no, I haven't made anything like that, but a couple of people have asked me about that, and so it's on my list of ideas. Okay, so let's talk, let's talk stack frame, because that's actually kind of important. In legacy mode, the size of an IDT entry determines okay. Right, so we already kind of covered these changes. Aside from error codes, wait, did I already copy this? I did not. Presents operating systems with a consistent interrupt stack frame across all interrupts. So that sentence is targeted at people like us right now. And that because otherwise, I think otherwise, yeah, like this this thing. I think you just had to know to like not access these members or something like this. So because I mean, JAWS pretty much only has user to kernel interrupts. So maybe that wasn't really a concern. And so pretty much because in JAWS, interrupts are disabled while running in the kernel. So it's not really possible to get an interrupt while running in the kernel, I think. Except for like fatal kernel page faults. You can get a fault, yes. Right. I'm thinking about this JOS OS specifically. I think in general, it disabled interrupts while it was in the kernel at all times, which means there weren't really a lot of opportunities to receive interrupts while in the kernel, with that exception of getting page faults in the kernel. But we didn't really do anything in that case. But in that case, you definitely should not, you just need to know to not access these members, because they would, I think they would go off the top of the stack, or no, they would just like, there's no stack change. And so anyway, these members just don't exist, are not allocated by the CPU. But this struct only has one representation. Okay, anyway, good to know about this. That handle interrupts generated by the int instruction can push an additional error code placeholder to maintain consistency. Okay. I mean, I understand the general concept of pushing the error code for interrupts that don't push an error code, and I think so. It seems like that stayed the same. In legacy mode, the stack pointer may be at any alignment when an interrupt or exception causes a stack frame to be pushed. This causes the stack frame and pushes okay. In legacy mode, your alignment is like whack, potentially. There are no alignment considerations, and therefore your stack can get super unaligned. And one of the things they fixed is that they aligned the stack pointer before pushing the stack frame to a 16-byte boundary. Okay, good to know. Compiler macros, isn't that unsafe on some system? The attribute packed. Well, okay, so macros are different from the attribute packed. Compiler macro. Oh, or you mean you're referring to is the packed unsafe on some systems? I think technically, well, it's not unsafe. It just expresses that you absolutely do not want any padding. I think this is a reasonable use of it. You have M general regs only. No, what does that mean? I've never heard of that flag before. Is that relevant here? Okay, so stack is aligned. Not that it really matters, but it's kind of just neat to know. Yo, what's up, Tugra? Nice to see you. The stack is aligned. The stack frame is itself is aligned. When the interrupt handler. Are these two sentences saying the same thing? I sort of don't. The stack frame itself, okay. Yes, since some compilers would generate code using SSC too. So in the interrupt code, you have to preserve the SSE register. Oh, I see. I don't know. You tell me. I'm using cross. Here's what I'm using. I don't know. I'm using no SSC, no SSC2, no MMX, no 3D. No, I don't know. I think I just like got these from somewhere. So, I mean, I think I had to add these because the kernel was like, no, the kernel was just like actually crashing because Clang was generating SSC instructions, but I think you need to enable support for them before you can run them, and I never did, so it just crashed anyway. So okay, so apparently there's this more like elite flag you can pass. M general regs only. That's crazy. So yeah, I mouse model using the Anker, I don't know, it's like shark mouse or whatever it is. Anker ergonomic mouse. Okay. The processor can arbitrarily... Yeah, no, I ran into that problem though, NSG. Yeah, I remember like running into that and needing to add those flags. Yeah, I don't plan to have SSE support for a very long time. So yeah, definitely not running that. The processor can arbitrarily realign the new RSP on interrupts because the previous possibly unaligned is unconditionally saved on the... Okay, this is like kind of confusing, but I get the main point though, that there's different alignment. Okay, aligning the stack permits frames to be aligned on a 16-byte boundary before interrupts are re-enabled. This allows the stack to be formatted, so speaking of XMM or SSE or whatever it is, for optimal storage, which enables to use faster loads. Oh, interesting. So, okay, this is we're deep in the weeds, but element one is only of consequence for the kernel mode case where there's no... Okay. Okay. Yeah, I sort of hate to do so much reading on stream, but it's kind of important actually, because it's reasonably different from 32-bit mode, and I also forgot how all this works. So IRET. So far we talked about the new IDT format, and some changes to how the stack frame is pushed. And now let's talk IRET. So IRET is how you return back from an interrupt back into whatever was running previously. And in the case of JOS, that's pretty much always returning back to user space. But right now, for the OS stuff I'm doing right now, I sort of I just don't have a user space, and I was just planning on trying to do some of this purely in kernel mode, like a no user space OS sort of thing. So that's sort of where I'm coming at it. So in our case, we're just returning back to kernel mode from kernel mode, and so there's no privilege changeable. Okay. IRET executes with an 8-byte operand. And again, what's the deal with IRET? So the way, back to this end pop TF, which is sort of like at least one example of how this worked with 32-bit. So like iret, right? Maybe it helps to first briefly remember like normal ret without the I. It's like a normal ret instruction. A normal ret instruction pops the stack into the instruction pointer, basically. 20 seconds, be right back. Right. Okay. Normal ret instruction pops a value off of the stack, and that value gets loaded into the instruction pointer, and that like redirects execution somewhere else. You use that to return from function calls. iret is sort of like normal ret, like on steroids. Rather than popping a single value off of the stack, it expects you to have like a bunch of stuff on the stack ready for it to pop. And it sort of expects like a bit of like a trap frame on the stack for it to pop stuff off, I believe. And I think that stuff is going to mostly correspond to this part. And so we can see in this code that it's popping AL, popping ES and DS. Right, we're popping all the registers. We're popping ES. We're popping DS. Skip, and we then adjust the stack pointer to skip trap number and error, which points the stack pointer back at the IP, which is just like how a normal ret works, but with iret, there's a bit more to it. It's the EIP and CS and flags, I guess. Check what we're saying. Far, ret, ret. Ret, far, ret, iret is the order of progression, I suppose. Far ret, that's like that segmentation return or something like that, right? That's like a bit more exotic, I think. But anyway, the whole idea is like you have like some stuff on the stack, and let's just use that as a bit of context to understand this. So iret pops 8-byte items. iret pops this. iret pops unconditionally only when it is executed in 64-bit mode. See, for it routines that exit. This is the part that we need to care about. There's like, it's sort of hard to read these documents because there's just so much kind of like cruft around compatibility and legacy. But basically the main point we're seeing here is that it's saying, okay, in 64-bit mode, it's always going to push the stack pointer and the stack selector. And then it's saying, okay, corresponding to that, when we iret, it's always going to pop these things from the stack frame. Okay, shadow stacks, blah, 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 don't really care or know what those are. Okay, this is crazy. Let's just kind of maybe quickly run through this at a high level. Okay, And then there's the reference, so that's sort of it. So I'm just gonna quickly browse through the rest of these things, and then we'll see what we can learn about that, and then we'll be in a good state next time to keep going with this. So stack switching. So the 32-bit architecture can automatically switch stack frames when an interrupt happens, typically if there's a privilege level change. Okay, and then 64-bit implement a modified version and an alternative. Okay, and that's what NSG was talking about earlier. He's like, you have a bit of the legacy, but there's also a new modern way to do stack switching on interrupt, which is the IST thing. What's up, Noxstar? Why are you building your own OS system? Pretty much just because I'm curious to learn more about how OSs work. And you tend to learn a lot if you try to make your own. So, okay. In 32 modes, the legacy thing is unchanged. In 32E, you know, I sort of don't know the difference between 32 and 30. I'm just going to quickly ask the AI. What's the diff between IA32 and IA32E? I think IA32E sort of means 64-bit mode, but I always found that really confusing. 32 is the normal 32-bit. 32E is Intel's 64-bit mode, also known as like all the normal things you might normally expect. Okay, thanks, Checkwab. So that's sort of what I thought. That is, yeah, that's such a cursed way of saying that. Oh my gosh. Okay. Right, so this is the thing NSG was saying. Legacy stack switch is modified when stacks are switched as, okay, as part of a privilege change. A new SS descriptor is not loaded. The emote loads only an inner level RSP from the TSS. Holy shit. The new is forced to null, and the selector's RPL field is set to the new. The new SS is set to null. The old SS are saved on the new stack. What a mouthful. I think my takeaway from that paragraph, the new SS selectors. Okay, if I were to like kind of like restate this, so my whole understanding of like, even at a higher level, what they're doing with 64-bit mode is they're trying to like kill segmentation. They're trying to remove segmentation from the architecture as much as possible and make it not even active. And so this SS selector is part of like all that whole legacy infrastructure that we're trying to not care about anymore. And they're just saying we're going to force the selectors to null because I think the selectors are just, they generally just map the entire address space anyway. And so they're like not really that relevant. It's not loaded. Okay, I think it's not super worth spending too much time on this. I saved on the new stack. We already sort of talked about that. In summary, a stack switch works like the legacy one, except the new SS selector is not loaded. Instance forced to null. Okay, thank you for summarizing that. Okay, this is some good pictures. Let's just save these pictures. So we're talking with privilege level change. We're on the stack. Okay, not that much. Is like RSP, RIP error code, and then the things about the conditional pushing of the RSP and NSS. All right, let's talk stack IST. Not gonna lie, Mac OS looks so clean for productive things on Linux. Yeah, I mean, yeah, I don't know. I like it. They hire professional designers to work on it, so I would hope they do a good job. I like it. Yeah. Dude, oh, probably Intel still got pissed that IA64 failed and AMD 64 got popular. Yeah, man, I would be pissed. I would be pissed if I invested like $1 billion in a new architecture and it failed. Okay. Interrupt stack table. So this is the new hot stuff that they added. So let's kind of learn about that. A new mechanism is available as an alternative. And NSG, since you seem to be here, do you use IST in Polaris, or are you using the legacy one? I would kind of guess you're using the newer one, but I don't know. This is what I'm more interested in. Alternative, the mechanism unconditionally switches stacks when it is enabled. So straight up off the bat, that is good to know. Because my understanding was that there's no stack switch in if the interrupt happened while you were in kernel mode, you would just keep running on the kernel mode stack. But it seems like with IST, you actually do switch stacks, even if there was no privilege level change. Use it for page faults and NMIs specifically, but not other interrupts. Interesting. I guess I don't understand why you would, when you would choose to use it for which kinds of exceptions. It sort of just seems like it's a newer, fancier thing to use all the time, but maybe not. So it can be enabled per interrupt vector. So for every different kind of exception or interrupt, you can choose whether you want the legacy one or the new one. So that's what NSG is saying. So you enable it on a couple particular exceptions. It's only available in this. It's part of the 64-bit mode TSS. The motivation is to provide a method for specific interrupts, such as NMI, to always execute on a known good stack. Oh, that's interesting. Because apparently that's a problem. If you are on some, like, if you're running, for example, if you're running in kernel mode on like some corrupted ass stack, and then a interrupt comes in, you are going to keep using that corrupted stack, and that's going to be kind of bad. And so it might be nice to force a stack switch. In legacy mode, interrupts can use the mechanism to set up a known by accessing the routine through a task gate located in the ITT. However, the legacy and scheduler. Usually when you have a specific situation where the stack shouldn't be shared or must be specific for one task or must not fail, you wouldn't want the stack used by a kernel task to be overwritten by the scheduler. Okay. Okay, that's interesting. So there's some specific circumstances where you I guess for the scheduler, and by scheduler, I guess, do you mean timer interrupt? I guess the whole idea of the scheduler timer interrupt is that you're sort of releasing the stack of the task that you were running on, and yes, and you just want to you want to like let that stack go, and not like mess with it and like run the scheduler on a totally different stack, because in that case you're going to schedule into like a new task on a different stack anyway, I guess. And so in that instance, it would make sense to like just really just like detach from that other stack, as opposed to trying to continue running the scheduler on it. So I think I kind of see that. And then imagine a double fault caused a problem with the kernel stack. You want to panic, is that right? And so that definitely makes sense to me. Like for certain very delicate interrupts or situations, you want to have maximum control over how good the stack is. And okay, that makes sense. Right. I've had issues where I incorrectly force a reschedule. So when the scheduler performed the context switch, it corrupted the original kernel stack and caused random crashes. Yeah, that sounds bad. You're gonna force a reschedule, so. Also, Ejib Jab in the Twitch chat. This is over my head now. I have to keep watching. You're welcome to stay and keep learning with us for sure. Yeah. I mean, honestly, a lot of this stuff is kind of over my head too. You can see me trying to literally wrap my head around it like in real time. But I think I get the main points of this. So, okay, so IST, fancy new mechanism, mostly built around safety. We wanted to have safer interrupt handling for more delicate situations in particular. 7 IST pointers in the TSS. The pointers are referenced by an interrupt gate descriptor. The gate descriptor contains an index that provides an offset into the IST section. Using the IST, the processor loads the value. Okay, so from what I'm understanding, you get space for 7 stack pointers. And so you can have like potentially 7 stacks or something like this. And then you can choose on a per interrupt basis which of them you want by putting an index into this list somewhere. Something along those lines. When an interrupt occurs, the new SS selector is forced to null. The old blah, blah, blah are pushed on the new stack. Interrupt processing, then if the IST index is 0, the kind of legacy mechanism is used. Okay. Interesting. So, okay, so actually, so maybe that's why it is only 7, because the first one, no. The first one is consumed by the 0, like the 0 index for kind of disabling IST. Okay, and blah, 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 shadow stacks, I don't know. I have no idea what a shadow stack is, so I'm not too concerned. Yeah. Yo, what's up, Abhishek Kratiri? Hi man, hope you're doing good. I got you live. Yeah, man. Thank you. Thanks for joining. And you caught me at just the time I think I'm going to try to wrap it up. So that was very intense reading the docs. But we haven't had an intense docs stream in a while. But that was good though, because I feel like there were some differences that are good to be aware of. So, so here's what it's going to look like kind of going forward. So I'm thinking we set up interrupts, and I think my goal, I would love to get some just basic task switching of kernel tasks going, like no user space, like no privilege level change, just do like some kernel threads or kernel task kind of stuff. And so that's going to involve two things. It's going to involve one, getting interrupt support working for the timer interrupt, although technically we could also do cooperative multitasking maybe, but interrupts in general would be good to get at the very least, so we don't boot loop anymore if there are kernel crashes. And so that's sort of a prerequisite for that. But then I'd like to get some basic kernel task scheduling going, because I'm kind of curious about how that works. So yeah. All right. Well, I think that's, so APIC, SMP, and interrupts next. I mean, SMP, I don't know if I'm going to be doing SMP super soon. Yeah, I mean, interrupts are the obvious one. APIC, I guess APIC for the timer, right? Yeah, probably like basic exception support, and then, yeah, maybe getting a timer interrupt working. I think I'm going to avoid SMP for a little bit though. SMP is, I mean, I definitely want to do that at some point, but I think it's a bit more advanced. Yeah, I mean, yeah, that's true. I mean, I have heard that advice before to have SMP implemented from the start. Yeah, that's a good point. And I guess it doesn't have to be that hard. Like I can have a global kernel lock and simplify things also. Yeah, I have heard the advice that it's good to design with SMP upfront. For anyone that doesn't know SMP, SMP is like multi-core support, like actual like parallelism in the kernel. So yeah. All right, y'all, I think I'm gonna kind of wrap it up here. And yeah, I wanted to say, please subscribe to my YouTube channel if you're not already subscribed. I would really appreciate that if you enjoy the context. Jib Jab, thanks a lot for joining the Twitch chat. If you're on Twitch, smash that follow. As usual, we also have the Discord. And so feel free to join us in the Discord. And I think that's pretty much going to be it. Yeah, Ismail, nice seeing you. Cheers. I hope you all have a great week, and I'll see you next week. Peace.